Okay, hello. So today we are finishing section 7.2. And I just wanted to remind you that we are omitting section 7.5. Okay, so we are focusing in section 7.2 on hypothesis testing for the mean when sigma is known and we have one sample. Now, our objectives for this section are to how to find and interpret p-values, and we already did that in class. We also did an example showing how to use p-values for a z-test for a mean when sigma is known. We're going to do another example, right? And then we're going to do these last two objectives here. Just as a reminder, or it's not a reminder, I think this might be new, but z-test is another way of saying perform a hypothesis test for the mean when sigma is known, or right. And z-test is actually the syntax that you use for your TI-83 and your TI-84. And so just as a refresher, you hit stat, then you go over to tests, and I think it is the first option, z-test. Okay, so that is how we will be performing our hypothesis tests in class. We're actually going to learn two different methods for hypothesis testing. One method is with rejection regions, and the other method is with p-values. So we already gave an example using p-values, and we'll learn a new method, which is using rejection regions. Okay, so let's get started. Where did we leave off? Flip through here. We did that example. Okay, so let's start here. According to a study, the mean cost of bariatric, which means weight loss surgery, is $21,500. You think this information is incorrect. You randomly select 25 bariatric surgery patients and find that the average cost for their surgeries is $20,695. The population standard deviation is known to be 2250, and the population is normally distributed. Is there enough evidence to support your claim at alpha equals 0.05? Use a p-value. Okay, so I've got this little sheet here that we'll fill out with the important information, and I also have a copy of the form that this is the form that we'll be using on the final exam. So I kind of want to go back and forth and show you how to answer the question in a way that would be appropriate for the final exam. Okay, so our first question is we have to figure out you are conducting a hypothesis test for the population mean or population proportion. Now, in order to figure this out, we go back to the statement. According to a study, the mean cost. So this right here, the fact that we've got mean, and then later on we have the word average. These keywords tell us that we are going to be looking at population mean. Okay, now what are the requirements for this test? So the requirements are, as we recall, the requirements for the test are we need to have sigma known. We need to have a random sample. And we need n greater than or equal to 30, or population is normally distributed. Okay, now what is the population that we're concerned with? The population is going to be all prices for bariatric surgeries. Okay, so maybe 19,000 is one price tag, maybe $19,375.24 is another price tag. Maybe $27,000 is another price tag, right? So all of the possible price tags, all the possible costs for bariatric surgeries is our population. And we are told that the population is normally distributed. So we are told here the population is normally distributed. We are also told that we randomly select, so this means our sample is random, and we are given the population standard deviation, right? So we can in fact go ahead and write this down. So the population standard deviation, sigma, is known to be 2250. You randomly select 25 bariatric surgery patients. That means N is going to equal 25. And the average cost for their surgeries is $20,695. So that means X bar is $20,695. Now notice that X bar is also going to be our test statistic. But first, let's answer this question, which is determine the null and alternative hypotheses and figure out which one is the claim. So in order to do that, we need to state the claim. What is the claim? So looking back, we've been told that you think this information is incorrect. So the claim is that mean cost of bariatric surgery is not $21,500. So let's write that down. Mean cost of bariatric surgery is not $21,500. How do we translate the claim into a mathematical statement? Mean, that's going to turn into mu. Is not, that's going to turn into not equal to sign. And then the 21,500.
It's 9:30.
We'll just write this as 21,500. We don't need to put a dollar sign. We don't need to keep track of units because it's written up here in the claim. Now, what is the complement of our mathematical statement? So the complement of mu is not equal to 21,500. Mu equals 21,500. Okay? Which one is H naught and which one is HA? Remember, the null hypothesis, H naught, is the mathematical statement that contains the equality. So it'll be mu equals 21,500. And the alternative hypothesis is the statement which does not contain the equality. So mu is not equal to 21,500. And lastly, the claim in this case is going to be the alternative hypothesis. Okay, so we are ready to put that in here. So our null hypothesis was mu is equal to 21,500. An alternative hypothesis, mu is not equal to 21,500. And the claim is the alternative hypothesis. Okay, so state the distribution to use for this test. We're going to use a z distribution because sigma is known. Okay, so now next we need the test statistic and the standardized test statistic. Because we're doing a hypothesis test for the mean, our hypotheses involve mu, and our test statistic is going to involve X bar. So X bar equals, let's go back and see what we, how to figure this out, $20,600. Let's put here $20,695. Okay. What is the standardized test statistic? Okay, so let's actually, and we've got room for it over here. So this is x bar equals 2695. So the formula for the standardized test statistic is z equals x bar minus mu divided by the standard error, which is sigma over square root of n. So this is x bar minus mu naught. So the connection between the test statistic and the standardized test statistic is the following. The test statistic is on your normal distribution, and we know that our sampling distribution is normal due to the central limit theorem. The standardized test statistic is the z-score of this test statistic. Okay, so the standardized test statistic shows up with the same area, the same cumulative area on the standard normal distribution as the test statistic does on the sampling distribution. Okay, so when we fill this in, let me actually just go ahead and be very clear about these numbers here. So x bar is the test statistic. Mu naught is the hypothesized mean. So this is what we are assuming the mean is, hypothesized mean. N is the sample size. Sigma, now by now, of course, everyone knows this, is our population standard deviation. And then lastly, this is our standardized test statistic. Okay. So when we plug all this in, we should get z equals x bar minus mu over sigma divided by square root of n. Okay. Now what is x bar? X bar is going to be 2695, right? And we got that from here. X bar is equal to 2695. What is mu? Mu naught, sorry. Mu naught, which is our hypothesized mean, we come over here, and it's this 21,500. This is mu naught. I think the calculator uses mu naught. The textbook uses K. Right, so this is the textbook. Refers to the hypothesized value as K. And the calculator, so TI-83 and TI-84, will use mu sub naught. Okay, so we got minus 21,500 divided by, what is our sigma? We need to go back here. Sigma we said is 2250, and n is going to be 25. So we'll have 2250 divided by the square root of 25. Okay, and when we do that, we should get, I believe we should get negative 1.79. So approximately negative 1.79. This is our standardized test statistic. So we'll put here z equals negative 1.79. What is the p-value? Okay, so we are ready to find our p-value. Now, you're going to go to your calculator, and again, on your calculator to determine the p-value, I'm assuming you have a TI, 83 or 84. Go to Stat, go to Tests, then use Z-Test. This screen is going to come up. The screen is going to have, the screen is going to first ask you to choose between data and stats. You want to make sure that you have stats highlighted because we have stats to enter. We don't have data to enter. We have stats to enter. For mu naught, we have 21,500. For sigma, we have 2250. For x bar, we have 20,695. For n, we have 25. And then there's this last little row, which has mu not equal to mu naught, greater than mu naught, less than mu naught. And here is your chance to determine, to tell the calculator what type of hypothesis test you're performing. Are you performing left-tailed, right-tailed, or two-tailed? We figured that out by looking at the alternative hypothesis. And so since the alternative hypothesis has a not equal to sign, we're going to be doing a two-tailed test. And here you should highlight, right, click this one right here. So make sure this one is highlighted. And then I think at the very end it says to calculate or draw. And you want to, of course, choose calculate. So choose your calculate. And your output should be a screen that looks like this, z-test. And it's going to have mu bigger than 21,500. It's just going to remind you of your hypothesized mean. It will actually calculate your standardized test statistic. So that's a nice little shortcut for you. It'll give you your p-value. Your p-value should be 0.0734. And it will remind you of x bar, which is 2695, and n, 25. Okay. So our p-value is 0.0734. Let's go ahead and enter that in here. So our p-value, p equals 0.0734. And in one or two complete sentences, explain what the p-value means for this problem. So here we go. The p-value tells us the probability of having a sample or of obtaining a sample statistic as extreme or more extreme than the one that we obtained. So let's see here. The probability of getting a sample of 25 bariatric surgery patients whose average surgery cost is as extreme or more extreme than what was ours. What was our average? Our sample average was $2,695. $20,695. Assuming that H naught is true. What is H naught? Assuming that the mean cost for bariatric surgery, mean cost, is $21,500, is 0.0734, which is 7.34%. Okay? So the probability of getting a sample of 25 surgery patients whose average surgery costs is as extreme or more extreme than $20,695, assuming that the mean cost is actually $21,500, is about 7.34%. That's what the p-value tells us. Now let's use the previous information to sketch a picture of this situation. We need to clearly label the horizontal axis with the test statistic and shade the regions corresponding to the p-value. Okay. So for us, we are going to have we're going to use our test statistic. So this is going to be a z distribution. And because our p-value is let's see here. Our p-value is 0.0734. So that means that the area in the tails So the area in the tails adds up to 0.0734, right? It's equal to the area in the left tail plus the area in the right tail, okay? Now, those tails correspond to this standardized test statistic. So negative, this will be negative 1.79, and this will be positive 1.79. And in the middle, we'll have 0, because this is a z distribution, and our inflection points will be at 1 and negative 1. Negative 1 and 1. Okay, so let's see here. So down here, so let's actually just put it here. Okay, so in the center, we know we have 0. And for our inflection points, we have 1 and negative 1. And now I need to go out to about negative 1.79. And out here to 1.79. And I need to shade to indicate that I'm doing a two-tailed. So I'm just going to shade it here. And shade this left tail. Okay. So we shaded the regions corresponding to the p-value. And our test statistic is right there. So now, make a decision to reject or fail to reject the null hypothesis. Now remember, alpha was 0.05, which is the same thing as 5%. And our p-value, so our p-value was 0.0734. So we had our p-value right here, 0.0734, and our alpha is 0.05. So we need to compare the two. So I'm going to add 2 zeros behind so I can have the same number of digits. And clearly p is greater than alpha. So my decision is going to be to fail to reject H naught. Reason for decision, p is greater than alpha. And finally, to interpret the decision, I need to look at, in order to interpret the decision, I need to look back at the setup. So my is HA, and I'm failing to reject. Look back at the chart. Not enough evidence to reject. Not to reject, sorry, to support the claim. To support the claim that the average price, average cost of bariatric surgery is different. Well, let's say is not equal to what do we have? $21,500. $21,500. Okay. All right, so there we go. Now notice for the back side of this page, we're actually not doing it. This would be for chapter 8 when we're dealing with 2 samples. Okay. So we've got this, yep. This is when we've got the same information here. Almost the same information. A lot of the information is similar. Okay. So that concludes our 2 examples of performing a hypothesis test using p-values. We are now going to learn about how to perform a hypothesis test using rejection regions and critical values. Okay, so let's introduce some new notation, some new definitions. A rejection region is the range of values for which the null hypothesis is very unlikely. Okay? And essentially we have a brand new decision rule. So our decision rule, let me write it down here, is very simple. So our new decision rule is reject H naught if test statistic falls in rejection region. I mean, it's pretty straightforward. If the test statistic falls in the rejection region, then you reject H naught. If the test statistic does not fall in the rejection region, fail to reject. H naught. Okay, so we're going to add some dividers here, because this first category, or the first results we get if we are using rejection regions. And I'm going to put as a reminder what we do if we're using p-values. So if you are using, when using rejection regions, this is what we get. When we are using p-values, we reject H naught if p is less than or equal to alpha. And we fail to reject H naught if p is greater than alpha. Let me actually double check that. It might be, so I'm going to actually put a star by it. It might be p is less than alpha and p is greater than or equal to alpha. So check your notes. To see, right? But it's either one of those two options. Okay. So we have a new decision rule, and the decision rule is very straightforward. You're essentially looking at if your test statistic falls in your rejection region. And we determine the rejection region by looking at critical values. Remember, we had critical values when we were dealing with confidence intervals, right? And we're going to find our critical values in exactly the same way. Exactly the same way. Okay, so a critical value separates the rejection region from the non-rejection region. Okay, so finding critical values in a normal distribution. Pretty straightforward. Once you specify your level of significance, alpha, so once you specify alpha, and you decide whether you're doing a left, right, or two-tailed test, you'll be able to find your critical values. Okay? Because here's the situation. If the hypothesis test is left-tailed, then here's the picture. So I'm going to draw the picture right here. So for a left-tailed test, that means we have something like this, right? And this area is going to equal alpha. So this number, that value, is your critical value. And to find the critical value, we would use inverse norm And then we put in our lower limit of negative 9999, our upper, oh, sorry, no, I'm getting it confused with the syntax for normal CDF. For inverse norm, we put in the area, which is our alpha, then we put in the mean, which is 0, and we put in the standard deviation, which is 1, and it will spit out our critical value. So that's for a left-tailed, okay? Now for a right-tailed distribution, you're essentially going to find the z-score that corresponds to an area of 1 minus alpha. And this makes sense because if you have a right-tailed hypothesis test, then you've got your shading is of the right tail, and your goal is to find this little your critical value, right? So your goal is to find that number, and this is what is question mark. This area is equal to alpha still, but in order to find question mark, you're going to use inverse norm. But remember, inverse norm only takes into account cumulative area. So the cumulative area, which is the area to the left, is going to be 1 minus alpha. So if we want to get this value, we need to put in here 1 minus alpha is our area. 0 is our mean, and 1 is our standard deviation, because that's still 0. This is still a z distribution. Okay. And now finally, if you have a two-tailed hypothesis test, then let's draw the picture. So for a two-tailed, you've got two tails, and the tails are symmetric. Okay? And this area, so this area is going to equal alpha over 2. And this area is equal to alpha over 2. Because the sum of the areas, the sum of the tails, is equal to alpha. And due to symmetry, each tail has an area of alpha over 2. So, to find the critical values, we would have two critical values in this case. Okay? And question mark is going to be inverse norm of alpha over 2, 0, 1. And our positive critical value is just going to be the negative version of question mark. Or you could also write inverse norm 1 minus alpha over 2, comma 0, comma 1. Because the cumulative area is 1 minus alpha over 2. Okay. So, you sketch your standard normal distribution, draw a vertical line at each critical value, and shade the rejection regions. So let's do this example right here. Find the critical value and rejection region for a two-tailed test with alpha equals 0.5. So we want a two-tailed test, and we want alpha equal to 0.05. So this means that we're going to have two tails. So I'll just say we've got a left tail and a right tail. I'm just estimating here. This area is going to equal half of alpha, and the area in the left tail satisfies the same property. Is equal to half of 0.05 divided by 2, which is going to be 0.025. Okay, so now I need to find this value and this critical value. So my critical value is going to be inverse norm of 0.025, comma 0, comma 1, which should be, I believe, negative inverse norm. Let's see, what do we get? So we want negative 1.96, I believe, is it? I think it is negative 1.96 for the one on the left, and the one on the right is going to be 1.96. So our critical values plus and minus 1.96. Okay. So I think that's what it should be. All right. So when we are, so we've kind of already discussed the decision rule based on the rejection region. When you're conducting a hypothesis test using a rejection region, you need to calculate your standardized test statistic, and then you also need to calculate your rejection region, right? And then you see, is your standardized test statistic in your rejection region, okay? So we have a repeat. The beginning process of the hypothesis test is exactly the same. You need to verify that you satisfy the appropriate conditions. The second thing you need to do is to find your null and alternative hypothesis and figure out which one is the claim. Then you need to identify alpha. Now, determine the critical value. You're going to use technology. Determine the rejection regions. That's going to be based off of your sketch. You're going to find your standardized test statistic, right? That's a computation. And once you have that computation, you'll be able to see, is Z in the rejection region? If so, we'll reject H0. If it's not, we will fail to reject H0. And then lastly, you're going to interpret the decision in the context of the original claim. So let's do this example here. Employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than that of sorry, this is a typo, it should say, is less than that of one of its competitors, which is 68,000. So, okay, a random sample of 20 of the company's mechanical engineers, so I'm going to start to write down that X bar is equal to 20, has a mean salary of $66,900.
It's 22 hours.
It's 10 o'clock.
Oh, sorry, I made a mistake here. N equals 20. X bar is equal to 66,900. Assume the population standard deviation, so assume sigma is equal to 5,500. I'm also supposed to assume that the population is normally distributed. So the population is normally distributed. I also need to verify that my sample is random and that I do have my population standard deviation. So I'm done with the first part, which is verifying, right? So I won't put this down, but what are the requirements? We need to have random sample, sigma needs to be known, and we need to have n greater than or equal to 30, or population is normally distributed. We are doing a hypothesis test for the mean. And now let's determine our null and alternative hypotheses. So let's try to find our claim. So what is our claim? Employees at a construction and mining company claim that the mean salary is less than $68,000. So the claim is that the mean salary of the engineers, mean salary of engineers is less than $68,000. Okay, I think that. So it might be that the employees are getting ready to come together and try to say, hey, we should have a raise, right? So let's see here. We've got our claim. Now translate the claim into a mathematical statement.